Greetings to all, and welcome back to the lecture series describing periodic properties of elements. In the previous lecture, you learned about the atomic radius of elements, which is the distance between an atom's nucleus and its valence shell. In general, atomic radii decrease from left to right across a period of the periodic table and increase from top to bottom down a group. We also spoke about ionization energy, which can be described as the energy required to remove an electron from a gaseous atom. The first ionization energy is smaller than subsequent ionization energies, and the first ionization of any atom removes a valence electron. The first ionization energies tend to increase across a period and decrease down a group. Finally, you learned about electron affinity, which is the energy released when an atom in the gas phase accepts an electron. Electron affinities tend to increase across a period. As with first ionization energies, exceptions to the trend can be explained based on the electron configuration of the element. By removing an electron from or adding an electron to an atom, we obtain ions, and in this lecture, we are going to discuss electron configurations and some other properties of cations and anions. You might recall from the introductory module on atoms, ions, and molecules that we can use the periodic table to predict the charges on many of the ions formed by main group elements. For example, elements in groups 1A and 2A form ions with charges of +1 and +2, respectively. Elements in group 6A and 7A form ions with charges of -2 and -1, and so on. As you probably guessed, knowing something about electron configurations enables us to explain these charges. Just as for atoms, we use the Pauli exclusion principle and Hund's rule to write the ground state electron configurations of cations and anions. As I detailed in the previous lecture, in every period of the periodic table, the element with the highest ionization energy is the group 8A element, the noble gas. Also, group 8A is the only group in which none of the members has any tendency to accept an electron. That is, they all have negative electron affinity values. High ionization energies and low electron affinities make the noble gases almost completely unreactive. Ultimately, the cause of this lack of reactivity is electron configuration. The 1s2 configuration of helium and the n(s2n) p6 valence electron configurations of the other noble gases are extraordinarily stable. It comes as no surprise that other main group elements tend to either lose or gain the number of electrons needed to achieve the same number of electrons as the nearest noble gas. Note that species with identical electron configurations are called isoelectronic, and to write the electron configuration of an ion formed by a main group element, we first write the configuration for the atom and either add or remove the appropriate number of electrons. Accordingly, the electron configurations for the sodium and chloride ions can be represented as follows. We can also write electron configurations for ions using the noble gas core to focus our attention on the valence electrons. Before we move on to some discussion about the electron configuration of cations derived from transition metals, I would like to remind you that the 4s orbital fills before the 3d orbitals for the elements in the first row of the d block elements. That is, it is slightly lower in energy. So, following the pattern for writing electron configurations for main group ions, we might expect the 2 electrons lost in the formation of the iron 2 ion to come from the 3d subshell. However, it turns out that an atom always loses electrons first from the shell with the highest value of the principal quantum number. In the case of iron, that would be the 4s subshell. Iron can also form the iron 3 ion, in which case the third electron is removed from the 3d subshell. In general, when a d-block element becomes an ion, it loses electrons first from the highest s subshell and then from the following d subshell. This explains, in part, why many of the transition metals can form ions with a +2 charge. When an atom gains or loses one or more electrons to become an ion, its radius changes. It should not surprise you that the ionic radius, the radius of a cation or an anion, affects the physical and chemical properties of an ionic compound. For instance, the three-dimensional structure of an ionic compound depends on the relative sizes of its cations and anions. In particular, when an atom loses an electron and becomes a cation, its radius decreases partly due to a reduction in electron-electron repulsions in the valence shell. We can also say that this leads to a reduction in shielding. A significant decrease in radius occurs when all of an atom's valence electrons are removed. This is the case with ions of most main group elements, which are isoelectronic with the noble gases preceding them. For example, consider the sodium atom, which loses its 3s electron to become a sodium cation. The valence electron of sodium has a principal quantum number of 3. When it has been removed, the resulting sodium cation no longer has any electrons in the third shell. Now, the outermost electrons of the sodium cation have a principal quantum number of 2. Since the value of the principal quantum number determines the distance from the nucleus, this corresponds to a smaller radius. On the other hand, when an atom gains one or more electrons and becomes an anion, its radius increases due to increased electron-electron repulsions. Adding an electron causes the rest of the electrons in the valence shell to spread out and take up more space to maximize the distance between them. The following figure shows the ionic radii for those ions of main group elements that are isoelectronic with noble gases and compares them to the radii of the parent atoms. Note that the ionic radius, like the atomic radius, increases from top to bottom in a group. In the end, if we look at the electron configurations of the oxygen dianion, fluoride ion, and neon, we see that they have the same electron configuration, forming an isoelectronic series. An isoelectronic series is a group of two or more species that have identical electron configurations, but different nuclear charges. Another important variation is that although these three species have identical electron configurations, they have different radii. In an isoelectronic series, the species with the smallest nuclear charge, or the smallest atomic number, will have the largest radius, while the species with the largest nuclear charge, or the largest atomic number, will have the smallest radius. To sum it up, in this lecture we explored the ions derived from transition metals and saw that when a d-block element loses one or more electrons, it loses them first from the shell with the highest principal quantum number. In other words, electrons in the 4s subshell are lost before electrons in the 3d subshell. You were introduced to the concept of ionic radius, which is the distance between the nucleus and the valence shell of a cation or an anion. A cation is smaller than its parent atom, while an anion is larger than its parent atom. We learned that the common ions of main group elements are isoelectronic with noble gases. An isoelectronic series consists of one or more ions and sometimes an atom, all of which have identical electron configurations. Within an isoelectronic series of ions, the greater the nuclear charge, the smaller the radius. In the concluding lecture of this module, we will examine periodic trends in the chemical properties of the main group elements. Thank you for your attention.